Hello everyone and welcome to MV Tutors. I'm Tolo and I'll be looking at the topic of physical and chemical properties of organic compounds. And without wasting any more time, let's get right into it. Oh, before I begin, please don't forget to subscribe to our channel, to like our videos, and if you want a tutorial session, you can go to our website mvtutors.co.za to book for a lesson. Okay, so before we get to the chemical properties, I'm just going to discuss the physical properties. And in order to understand the physical properties, we're going to look into the intermolecular forces. Okay, so by intermolecular forces, that's where we're going to start. I'm going to just refer to intermolecular forces as IMF. Okay, so the compounds that we have for organic chemistry is mainly oxygen, mainly carbon and hydrogen, and then you have oxygen in some cases. So I'm just going to discuss the intermolecular forces between those and the types that we can expect. All right, so the intermolecular forces. Okay, the intermolecular forces acting between different molecules, okay, actually the van der Waals forces. You would have learned these in grade 10 and grade 11, but they were introduced in grade 10, if memory serves me correctly. So yeah, van der Waals forces. Okay, and the two types that we'll be looking at specifically are the hydrogen bonds. Ooh, can't spell hydrogen. Okay, the hydrogen bonds, which by the way are quite strong. Okay, and then we're also going to have a look at induced dipole forces. Okay, so with the induced dipole forces, you also get dipole forces. Okay, induced dipole forces or dipole forces. Okay, so what do we mean by induced dipole forces? Like I said, you should know this from grade 10, but just a little bit of a recap. Okay, so induced dipole forces, let's say you have an alkane. An alkane by nature is polar. Why? It's a hydrocarbon. It consists only of hydrogen and carbon atoms. So your carbon atoms are surrounding the carbon chain. And because of that, because you have hydrogen on the outside, it's non-polar, okay? So when you have induced dipole forces, you're gonna take one polar molecule, let's say an alkane. So you're going to take two of those alkanes, and then when you bring them together, okay, so what happens is momentarily the electrons, remember electrons are the ones that are responsible for the bonding and so forth. The proton and nucleus are just protons and neutrons are just safe in the nucleus, but there in the outer shell you have electrons that are responsible for bonding. So when now you have two alkanes which are polar, and you want to have them react, so they will temporarily be non-polar. You'll have electrons shifting, okay? So then within that within that non-polar molecule, your electrons, as they shift, okay, one part of it will be positively charged, the other part will be negatively charged. So for that moment, it will be polar. So that was what we mean by induced, meaning you induce the polarity within that non-polar molecule. And as a result, those are weak forces, because as soon as now those alkanes, for example, are moved away from each other, then they go back to being non-polar. But if you bring them together and force some sort of reaction between them, then they become temporarily polar, and then they can then form reactions. Okay. Dipole forces, well, you have those weak polar molecules. They're not necessarily that strong. Okay, there's a way of calculating polarity between molecules. So if you realize that this one is quite weak, okay, and you bring those two weak polar molecules together, they form dipole-dipole forces. And because the polarity is quite weak, it's not a strong polar molecule, it is a weak force at the end of the day. So it's a van der Waals force that is weak. So your induced dipole forces as well as your dipole-dipole forces, they are weak. Then you get to your hydrogen bonds. The bond, think about water, okay, where you have oxygen and hydrogen atoms. So hydrogen bonds, we normally refer to your oxygen and hydrogen atoms, okay, they're very strong. The polarity between them is also quite strong. So you know when you have hydrogen bonds, you have a tight molecule there, which will be hard to break, hard to separate. Whether you increase the boiling points are increased, the melting points are increased, because it's that tight. It's very difficult to break apart. So those, when we discuss the intermolecular forces between organic compounds, we will be referring to hydrogen bonds, induced dipole forces, and dipole-dipole forces. All right. So yeah. And then, what are the physical properties that we'll be looking at exactly? Okay, so let's start with the physical properties. Okay, so we will be looking at the phase of your organic compound. Is it liquid? Is it gas? Is it a solid? Okay, then we're going to look at your melting point. I'm just going to say MP. Okay, so melting point is the temperature at which your substance goes from a solid to a liquid. Okay, then we're going to look at boiling points. Okay, and that is where the temperature at which your substance goes from a liquid to a gas. Okay, we're going to look at vapor pressure. I'm just going to say VP. Okay, your vapor pressure is basically the pressure that you have from a gas or vapor. We normally refer to vapor as a gas. So the pressure that you get from your gas, okay? Yeah. And then what else are we going to look at? So we're going to also look at viscosity. Ooh. Okay, viscosity, density, and solubility. Ooh, solubility. All right, so solubility is basically, for example, if you have like salt, which is sodium chloride, and you add it to water and you stir it. So basically, do those sodium chloride ions or sodium ions and chloride ions, do they react with the hydrogen and the oxygen atoms within the water? And obviously if the solution is clear, so your solute is your salt, your solvent is your water, and when they mix together and they're kind of clear, or you don't see the original particles anymore, then you have a solution. Okay, density, well, that is mass over volume. You basically want to know, I mean, a highly dense, I could think of gold, or most solids. Gold is quite heavy. So gold is more dense than what? Maybe carbon, for example. So gold is more dense than it is for carbon. All right, so basically, how much of a substance do you have per volume? That's density. All right. Ooh, I didn't even spell viscosity correct. Okay, I missed a C there. Okay. Yeah, viscosity. So basically those are your physical properties, but we're really going to focus mainly on these first four: your phase, your melting point, boiling point, and vapor pressure. And you can actually summarize it by saying the following. The higher your intermolecular force, okay, or the stronger your intermolecular force, okay, the higher your boiling point is, okay? The higher your melting point is, okay? And the lower your vapor pressure is. If you know this, guys, guys and girls, if you know this, you are kind of sorted. So the stronger your intermolecular force, the more difficult it is to break the bonds apart. So you're going to need a high melting point. You're going to need a high boiling point. Okay, your vapor pressure, not so much. I mean, vapor is as a result of your substance or your liquid heating up and forming gas. Okay, so if it takes that much for it to boil in the first place, it means your vapor pressure is going to be low. Okay, so your vapor pressure is indirectly proportional to your intermolecular force. All right, and the opposite applies. The lower your intermolecular forces, like the induced dipole forces and dipole forces, well, the lower your boiling point will be. It won't take that much to boil it. It won't even take that much to melt it, but your vapor pressure will be high. Okay, so let us look at what really affects your physical properties, okay, concerning your organic compounds. Okay, so with the chemical properties, we're going to look at the functional groups, okay, and I'm starting with the hydrocarbons, the alkanes, alkenes, alkynes. Okay, so with the alkanes, they are saturated, okay, so by saturated, it means you can't add any more atoms to these compounds, all right? And because they are saturated, they are most likely not keen to react with other compounds. Okay, so they're somewhat unreactive, if there is such a word. I think let me just get the proper term. Okay, so they are unreactive. I think let's just put it like that. So because of them being saturated, they are unreactive, generally unreactive. Okay, but when it gets to alkenes and alkynes, they are unsaturated. Okay, unsaturated. So because of their double bonds and triple bonds, they can get more atoms added to them. Okay, so yeah, through the process of addition reaction. So they are unsaturated, and because they are unsaturated, they like to react. Yes, we can say they are reactive. Okay, what else can we say about the alkanes? Okay, so basically they have weak van der Waals forces. Okay, so yeah, so their intermolecular force is quite low. And remember, we did talk about it, that what is the effect of your functional group on the physical property. And then we said that alkanes, alkenes, alkynes, yes, your hydrocarbons form part of those that have weak intermolecular forces. Okay, so yes, they both have, or all of them rather, have weak intermolecular forces. And what else can I say about them? Yes, your alkanes, guys, those are non-polar. Okay, because you have your hydrogen atoms surrounding your carbon atoms, so you pretty much, there isn't any polarity there. You don't get one side being negative and the other side being positive. It's positive all around because of the positive H atoms that are surrounding the carbon. Okay, and your alkenes, your alkynes, well, they are yeah, there's nothing much to say about them, but all of these, your hydrocarbons, they're actually quite volatile. Okay, your alkenes and alkynes mainly are produced through cracking. Okay, so in the video about organic compound reactions, you'll hear about cracking and what it is. So yeah, that's pretty much that regarding the hydrocarbons. And then now we're gonna look at your haloalkanes. Okay, so with the haloalkanes, that's pretty much when you have an alkane, but instead of having a hydrogen atom, you replace it with a halogen. Remember, your halogens are like chlorine, bromine, iodine, fluorine. Okay, so those are halogens. So yeah, you've replaced one of your hydrogen atoms with a halogen and you get a haloalkane. With them as well, guys, remember, it has lower intermolecular forces. Okay, they have weak forces between them. All right, and then in terms of polarity, you get some that are polar and some that are non-polar. Okay, if it is non-polar, it means, like as I explained with the alkanes, that you have your carbon atoms and you have your hydrogen atoms all around it, which is positively charged all around. So that is when it is polar. But if it's, sorry, when it is non-polar. But when it is polar, okay, you can have one part of your organic compound that is negatively charged, and another part that is positively charged. So haloalkanes, it depends. All right, so maybe on one side you would have fluorine, okay, bonded to your carbon, and on the other side you have your hydrogen. So when you calculate the polarity between fluorine and carbon as opposed to the one with hydrogen and carbon, you'd find that maybe the fluorine and carbon has a high electronegativity overall. So that side where your halogen is, probably it's more negative, but the side where your hydrogen is more positive, and therefore you have a polar compound. Okay, so that is it with haloalkanes. And another thing with haloalkanes is they are quite poisonous. Okay, so the higher the content of your haloalkanes, I'll just mark them with an X. Okay, the higher the content of your haloalkanes, the more poisonous your organic compound will be. With your hydrocarbons, that's where you normally get like your paraffin, your petrol, and all of that. So that is why I did say that they are highly volatile, highly flammable as well. But with haloalkanes, they are like poisonous. The higher the content of your halogen, more poisonous it is likely to be. Okay, yeah, and then what else did I miss? Yeah, that's basically that. Now we come to alcohols. Okay, with alcohols, guys, remember you have your OH, your hydroxide, and as soon as we mention hydroxide, you know that you're gonna get strong intermolecular forces, right? Because of your hydrogen bonding. So you're gonna get strong intermolecular forces because of hydrogen bonding. Okay, and with your alcohols, okay, they're mainly in liquid form. Yes, your alcohol. Well, actually, the ether or ethanol, ethanol is the one that is responsible for making beer, um, your alcoholic beverages. Let me just put it that way. That is, yeah, your ethanol, okay? But your methanol, that one is poisonous, so don't go ahead and drink it. Remember, meth, it is one carbon with three hydrogen carbons and an OH bond, okay? So, and then ethanol, it has two carbons. So that is the one that is responsible for your alcoholic beverages. Okay, and alcohols are saturated. Okay, I think the only organic compounds that are not saturated are alkenes and alkynes, but haloalkanes are also saturated, as well as your alcohols. You have strong hydrogen bonding between them, and they are generally soluble. Okay, yeah, they are generally soluble, and yeah, That's that with the alcohols. Then you have your ketones and your aldehydes. Okay, if you've watched the video on isomers, you will know that ketones and aldehydes are actually functional isomers. Okay, so they are functional isomers of each other. All right, so they have similar properties basically. With ketones or with an aldehyde, it's just that you have your carbonyl group at the end on the first carbon, and with your ketone, you have it somewhere in the middle. Okay. Yeah, it's not at the ends like your aldehydes, it's in the middle. Okay, so you have aldehydes. Yeah, so they are both functional isomers of each other. Your ketones actually produce pleasant smells, okay? So yeah, generally they produce pleasant smells, pleasant aroma. Okay, let's just call it a pleasant aroma. But your aldehydes, it depends, okay? So with short-chained aldehydes, you do get pleasant smells. But your long-chain aldehydes, my handwriting, they are not so pleasant. It smells bad, so it's like bad odor. Did I spell that correctly? Or rather, unpleasant smell for the aldehydes if they have long chains, okay? And, okay, so ketones and aldehydes both have weak intermolecular forces, okay? So, yeah, they have weak induced dipole forces, but they both have strong, or rather stronger compared to the weak forces, okay? Not stronger in general, stronger dipole forces. Okay, let me just... So for both ketones and aldehydes, the longer chained ones, so longer chains, okay, they are insoluble, okay? So they are like if you put a rock in water, it's just gonna sit there. Okay, it's insoluble. Okay, but the shorter chains, I'm just gonna say short chain, they are soluble. Okay, so those are your ketones and aldehydes. And then the last group, two groups we're gonna look at, carboxylic acids and your esters. Okay, so your carboxylic acids as well as your esters, they are also functional isomers, okay, of each other. All right, but when it comes to your intermolecular forces, your carboxylic acids, because of the OH bond that you have there, they are strong, okay? So they have stronger intermolecular forces, whereas your esters, because of esters not having hydrogen bonding, the intermolecular forces are weak. Okay, both of them are saturated. Like I said, the only unsaturated of the whole functional groups we've discussed are your alkenes and alkynes. Okay, yeah. So yes, with your carboxylic acid, you have your intermolecular forces that are strong because of the hydrogen bonding. But in some cases, I mean, even with alcohols, you have your carbon chains, right? Then you will have your hydroxide for carbon. So on that portion of the hydroxide, that's where you have strong hydrogen bonds. But for the rest of the carbon hydrogen atom bonds, you still have weak intermolecular forces there. Okay, so the same with carboxylic acid. Only where you have your hydrogen bond, your OH, that is where it has strong intermolecular forces. But the rest of the carbon chain, it is still weak when it comes to its forces. But in general, carboxylic acids do have strong intermolecular forces as well as alcohols. All right. So yeah, what else? Carboxylic acids are soluble in water. Okay. And for esters, well, it's only short chains that are soluble in water. Okay, so short. Okay. Now, when it comes to the boiling points of carboxylic acids and esters, okay, well, the boiling point of carboxylic acid, we're expecting it to be high because of the high intermolecular forces. Okay, so it is, your carboxylic acid, you do have high boiling points, okay. Their boiling points are actually quite similar to aldehydes and ketones with the same molecular mass, okay. So if you're to compare boiling points of your ketones, your aldehydes, as well as your carboxylic acids, but with them having the same molecular mass, then yes, you do get similar boiling points. All right. With esters, on the other hand, yes, it is. Well, the boiling points are lower than the carboxylic acid, but you also do get similar boiling points to your aldehydes and ketones. Okay, but it is lower. Okay, so yeah, the boiling point is lower than the alcohols and carboxylic acids. Okay, so that's the thing, because of the hydrogen bonding not being there, you do have lower boiling points, and those boiling points for the esters are actually lower than your alcohols. Lower than alcohols and carboxylic acids of similar molecular mass. Okay, so yeah, your boiling points of carboxylic acid, they are similar to ketones and aldehydes of the same molecular mass. The boiling point of esters are less, almost similar but less than the alcohols and carboxylic acids of similar molecular mass. And that sums it up for the chemical properties of your organic compounds. We're going to look at an example now. All right, so we're going to have a look at a paper from the 2017 March paper 2 paper. Okay, question 3. So it says learners investigate factors which influence the boiling points of alcohols. They use equal volumes of each of the alcohols and heat them separately in a water bath. The temperature at which each boils is measured. Okay, the results obtained are shown in the table. So butane 1-ol, pentane 1-ol, and hexane 1-ol. So we know bute has 4 carbons, pent 5, and hex has 6. And the fact that they say 1, it means it's on the first carbon. Okay, so we're dealing with primary alcohols here. Okay, so now it says to define the term boiling point. We had already covered that, so I'm not going to write it down. I'm just going to say it. So, right, it's the temperature at which a substance turns from a liquid to a gas, or you could say it's the temperature at which vapor pressure is equal to atmospheric pressure. Okay, so we're done with that. And then 3.2, what property of alcohols requires them to be heated in a water bath? That's something that I actually didn't cover as I was doing the chemical properties. But alcohol is quite flammable. Okay, so yeah, you want to heat it in a water bath and not exactly apply direct heat or fire to it to heat it up. Okay, so the property is that it's flammable. Okay, and then 3.3, the boiling points of alcohols are compared with each other. Okay, what structural requirements must the alcohols meet to make it a fair comparison? Okay, I had mentioned it before. So here you have primary alcohols. Okay, so first of all, these alcohols are in a straight chain. Okay, yeah, so it's a straight chain. Okay. Ooh, yeah, it's a straight chain due to them being primary alcohols. Okay, so a primary alcohol is basically where you have a hydroxide group at the end. Okay, either on the first chain, well, it will be on the first chain. We don't necessarily put it at the last chain. But yes, if it were a secondary alcohol, it would be somewhere in between. Okay, then it's kind of forms a branch. Also, a tertiary alcohol, it forms like two branches. So you want this thing structurally to be a straight chain. Okay, and that is achieved by having a primary alcohol. Now they say fully explain the trend in the boiling points. Okay, so as you can see, the more carbon atoms you have, okay, the higher the boiling point. Okay, that is what we're seeing. We have more carbon, it increases. You have butanol, you have pentanol, you have hexanol, and at butanol it's 117, pentanol 138, hexanol 157. So the more carbon atoms you have, or the longer your carbon chain gets, the higher your boiling point. You can also say the higher your melting point will be, but we're not discussing that. But you could also say that your boiling point increases because your intermolecular forces get stronger. So the higher molecular forces are, the higher your boiling point will be. The longer your chain is, the higher your boiling point also gets. Okay, so that is the trend that we are seeing. Okay, so yeah. Okay, so that is 3.3. Now 3.4, how will the boiling point of hexanol be affected if the volume of hexanol is doubled? Okay, so choose from increase, decrease, remains the same. Okay, so from the properties that we talked about, there were 5 of them that we spoke about that actually affect the physical properties of organic compounds. We first spoke about the intermolecular forces, the chain length. What else did we talk about? We spoke about whether it's a branched hydrocarbon or just a straight hydrocarbon. The length, yeah, we did speak about the chain length. Let me go back. I don't have to cram it. Okay, so carbon, the branched carbon atoms, molecular mass, chain length, the functional group, yeah, the intermolecular force. So that is what would affect the physical properties. Okay, volume in this case doesn't affect it at all. So the boiling point will not be affected by volume. So whether you increase the volume, you decrease the volume, although for the experiment they made sure that they have the same amount, the same volume, they kept that constant, but honestly it doesn't change it. So it remains the same. Okay, only the 5 that we mentioned will have an impact on the boiling point. Okay, so 3.5. In another investigation, the learners compare the boiling points of hexane 1-ol and hexanol. Okay, Okay, so be careful here, guys. Here you have an alcohol. Okay, OL, alcohol. But AL, that is an aldehyde. Okay, an aldehyde, similar to ketone. They are functional isomers. Yes, that one, aldehyde. So now you have hexanol and you have hexanol. All right. So if you're going to compare these two, I'm already thinking alcohol, because of the hydrogen bonding, that's strong. It has a high boiling point. But a hexanol, it's one of those weak van der Waals forces. But anyway, 3.5.1, it says, write down the independent variable for this comparison. Remember, you have the independent and the dependent variable. For example, your y-axis and your x-axis. Your x-axis is independent, and your y-axis, that's where you have your your x-axis is independent and your y-axis is dependent. Okay, so the values you get on your y-axis, they are highly dependent on the x-axis values. So what is the independent variable for this comparison? Well, that will be the functional group. Okay, so I'm just gonna write these ones down. So if you had a graph there, you would have your functional group here, and then you'd have your boiling points there. So what happens if you have an aldehyde? Would your boiling point be high? If you had a ketone, if you had an alcohol, how will that relate? So your boiling point, that depends on your functional group. So your independent variable is the functional group. Now 3.5.2, they find that the boiling point of hexanol is higher than that of hexanal. All right, so explain this observation. Again, with your alcohol, you have high intermolecular forces or strong intermolecular forces because of the hydrogen bonding. Okay, and because of that, you're going to have high boiling points, high melting point, lower vapor pressure. All right. Yeah, you can't really say much about the structure because the structure is pretty much the same. You have a long chain. Your aldehydes, they also have their carbonyl group at the end, just like your primary alcohol. It's not like a ketone where it has it somewhere in between. Okay, so your aldehyde as well as your primary alcohol, they have a similar structure. Okay, it's just you have a carbonyl group for aldehydes and you have a hydroxyl group for alcohols, but it all goes back to the intermolecular forces. And with alcohols, because of the hydrogen bonding, it has high intermolecular forces. Therefore, you have high boiling points. But with your aldehyde, on the other hand, you have lower intermolecular forces. Okay? And your boiling point is therefore low. Yeah, what else can I say about it? Well, yeah, you could also talk about the energy required to break the bonds. So for alcohols, you are going to require high energies to break the bonds apart. But for the aldehyde, you need less energy to break the bonds apart. And yeah, and that is it. So that concludes our session for the day. So yeah, if you require any tutoring, please do visit our website www.mptutors.co.za and make a booking. And don't forget to like this video, subscribe to our channel as well. Thank you.